let us do this. So, sigma omega dot I triple dash into HFI will be equal to, now we will expand this product omega dot PR triple dash into HF products. Products CO2 H2O, they have heat of formation, so non-zero. So, that into the rate at which products are produced. So, that similarly fuel has heat of formation which is non-zero, that into rate at which fuel is consumed. Okay. So, that you have to add, but I should actually add omega dot OX into HF OX, but this is 0. HF is 0, so that I need not add that. So, these are the two terms which will result from this summation. So, now you can see that the rate at which products are produced is omega dot triple dash PR, rate at which product is produced. What is that? It will be equal to, that is equal to this. So, we can say omega dot PR triple dash will be equal to minus of 1 plus S times omega dot triple dash F. When 1 kg of fuel is consumed, 1 plus S kg of products is formed, correct? Because 1 kg of fuel reacts with S kgs of oxidizer to form 1 plus S kg of products. So, now here 1 kg of fuel is consumed. So, I have to put negative sign here into 1 plus S, that will be the rate at which the products are formed. Okay. So, now this W, the omega dot triple dash PR is written as minus 1 plus S times omega dot triple dash F plus second term written plus omega dot triple dash F into HF. So, taking the omega dot triple dash F outside, this HF of fuel minus 1 plus S times HF of products. This is the heat of combustion, delta Hc. So, omega dot triple dash F into delta Hc, that will be the this term, summation of omega I triple dash into HFI. So, that will be this heat of combustion times the rate at which fuel is consumed. Okay. So, that is this term. So, now if we do this, then so why I am arriving at this, because I invoke this, when unit mass of fuel is burnt, S times of that of oxidizer is consumed, 1 plus S times of that of products is formed. Okay, that is the criteria used. So, now write the energy equation in this way, that is rho Cpu into dt by dx, convective term equal to d by dx of rho d Cp. So, lambda thermal conductivity by Cp equal to rho d. So, thermal conductivity equal to rho d Cp. So, that is what I have written here, rho d Cp is thermal conductivity into dt by dx minus this. So, this I have to minus this summation term will be equal to this term. So, I am just substituting here this. So, this is the energy equation. So, we have 3 equations for the species conservation, any 2 you can use. Okay. So, this 3, out of this any 2 can be used here. Okay. So, now this plus energy conservation is this equation. So, now please understand that how will you now eliminate the source terms. How will you do that? So, if you consider a variable like this, YF minus YOX divided by S. So, now what I do is I take this equation, this is equation 1. Okay. Now, this equation I will multiply by 1 by S. The second equation I will multiply this by 1 by S. First equation is y of this equation, I will not do anything. This minus 1 by S times this. Okay. Then I can write the transport equation as this. The left hand side will be rho u for that combined equation, rho u d YF minus YOX by S by dx equal to d by dx of rho d is common. So, rho d into d YF minus YOX by S. So, these two terms no problem. So, that variable will come, but now the source term will transform as omega dot triple dash F minus omega dot triple dash of OX divided by S. Okay. Now, you understand that this is the equation, 1 kg of fuel plus S kg of oxidizer will form 1 plus S kg. That means if 1 kg of fuel is consumed, S kg of oxidizer will consume. So that means if I write omega dot triple dash F minus omega dot triple dash OX by S, this will be equal to 0. Correct? So that means when I combine the variable as YF minus YOX by S, the source term in that equation, when you substitute for YF minus YOX by S, you will get this source term omega dot triple dash F minus omega dot triple dash OX by S. This will be equal to 0. That means the source term goes to 0. So YF is not a conserved scalar, YOX is not conserved scalar, but a combination of these two, YF minus YOX by S, defined for this equation will be a conserved scalar, because the rate at which fuel is consumed will be the rate at which oxidizer is consumed divided by its mass, S. So when you subtract these two, it will become 0. Correct? Similar way we have written here in this, the rate at which product is formed is nothing but the rate at which fuel is consumed multiplied by the mass of the products, or we can write this as omega dot F triple dash will be equal to, or minus of this will be equal to omega dot triple dash PR divided by 1 plus S. Correct? So because of the statement, this into this single step chemistry. Okay. So we can see this as this is a conserved scalar now, because no source term. Similarly, if you write YF plus YPR by 1 plus S, as I told you, omega dot F, okay, plus omega dot triple dash, so this is triple dash F, this is PR by 1 plus S will be equal to 0, because this is a relationship here. Sorry, here this is the relationship here. So minus omega dot triple dash PR by 1 by S will be equal to minus of omega dot triple dash F. So this will be equal to minus of omega dot triple dash F. So this will cancel out and become 0. So this is a scalar which is conserved because there is no source term. Similarly, when you can combine the one of the mass reaction, say YF, into multiply that equation, YF conservation equation, with delta Hc. Okay. So here this term rho u YF into delta Hc, this entire equation I multiply by delta Hc, and this is added to this equation, energy equation. Okay. So I have rho u d YF by dx equal to this total this equation now will be equal to d by dx rho d dyf by dx plus omega triple dash F. So this I will multiply by delta Hc and add to this. I am adding these two. I will get a source term for this as omega dot F triple dash delta Hc from this equation minus omega dot triple dash F into delta Hc from this equation, which will equal to 0. So this Cpt plus Yf into delta Hc again becomes a conserved scalar because the source term cancels out. So these are the way we define a conserved scalar. When I say I define these three variables as a B variable, okay. So let us say B equal to Yf minus Yox by S, or B equal to Yf plus Ypr by 1 by S, or B equal to Cpt plus Yf into delta Hc, then I will have the equation for B only as this without the source term. Rho u dB by dx equal to d by dx of rho d into dV by dx. So the second order governing equation without nonlinear source term is solved with appropriate boundary conditions, and you can get, so define B as one of this variable, calculate this and get a preference for B. Similarly, define B as another variable and get. So once you solve for this, okay, and this and all the three, you will get you can retrieve back the, so by the distribution of B we can retrieve back the primitive variables which are YF, YOX, YPR and T can be retrieved. Okay. The advantage of this is we do not need to solve this using a source term. There is no source term here. So, that is the advantage of this. Even though I simplify the equations like this, here the complexity has not reduced because of the presence of the source terms, nonlinear source terms. But by defining a variable like conserved scalars, I get an equation without nonlinear source term. I can solve it easily. Okay. So, I can do this and solve for, say, let this be B1. I can call it, so this is B1 and this second will be called B2 and third will be called B3, and I solve for B1, B2, B3, then I can retrieve back these variables. But solve it by appropriate boundary condition. So, B1 will have a boundary condition based upon fuel and oxidizers mass fractions. Similarly, B3 will have temperature based boundary conditions also in addition. So, based upon that you can solve this. Okay, now, so here you can see that the B will vary in a range. Mass fractions normally will vary in, for example, the first two if you use it will vary in the range of say 0 to 1, but if you take B3 it will vary from say 298 to flame temperature. So, you can see that tremendous amount of variation is there. So, is there any way to normalize this? That is what we are trying to do here by defining what is called a mixture fraction. When I define a mixture fraction, what I assume is, like let us see this. So, I want 1 kg of products. So, some fraction of fuel, fraction of 1 kg I burn, F kgs of fuel, okay. Then 1 minus F is the stoichiometric air required for this. So, 1 minus F kgs of oxidizer giving 1 kg of product. So, that is the equation I consider, for example. But you can see that there is a flow process where F kgs of fuel flows into the control volume through one of the inlet. Then 1 minus F kg of oxidizer flows in through the another inlet, and finally 1 kg of products are formed and they exit through another exit port. So, now any extrinsic property E I will take, okay, or it may be a specific property also. So, I take any property associated with the flow, and what I do is I can write this, okay, F times E suffix F plus 1 minus F times E suffix A equal to E suffix M. What is this? This is the properties value. E suffix F is the property value at the fuel stream. Similarly, E suffix A is the property value at the air side or the oxidizer side. Similarly, I say mixture, which is the product finally, correct. So, EM is the property of the mixture on, or when complete the reaction is finished, it will be the property of the product. Okay. So, this equation holds good, correct. So, now based upon this equation, I define F as property at the mixture stream minus property at the air side or the oxidizer side divided by property at the fuel side minus property at the oxidizer side. When I do this I call mixture fraction. Do you understand? So, now the property can be anything, as I told you. I can have property, the property is a conserved scalar. So, that is what we already defined the conserved scalar. So, let us take property as YF minus YOX by S, one of the conserved scalars. I can write also Cp. So, E can be also Cpt plus omega dot triple dash F times delta Hc, sorry, not this, YF into, okay. So, this can also be called, so here what we defined in this here. So, this can also be one of the E values, property values. So, when you use this, then you can see that F is a normalized variable, will vary from 1 at the fuel stream and it goes to 0 at the oxidizer stream. That is, so that is the definition of mixture fraction. So, now based upon this, any variable you can take. Now I can write, so let us take this for example, YF minus YOX by S, then F can be defined as what? YF minus YOX by S at the mixture stream minus the same quantity at the oxidizer stream divided by the difference between YF minus YOX by S at the fuel stream minus that of the oxidizer stream. So, this will be the mixture fraction, but you know that at fuel stream, let us take fuel stream, YOX will be 0 at the fuel stream. Okay. So, if complete combustion takes place, YF and YOX will be consumed. Okay. But let us just take this. Similarly, definitely since fuel is supplied through a particular inlet, okay, separate inlet, oxidizer is supplied through a separate inlet. So, YOX will be 0 at the fuel stream. Similarly, YF will be 0 in the oxidizer stream, that is for sure. So, when you say the oxygen stream, this will be 0 here, this also will be 0, correct, but in the fuel stream this will be 0, that is it. Okay. Now, what will be the value of YF in the fuel stream? This will be equal to 1, only fuel coming out of this, so this will be equal to 1. So, I can write this as 1 plus YOX by S in the denominator, and in the numerator YF I am eliminating, and in the mixture I have both YF and YOX. Okay. That means that in the mixture, until the complete combustion takes place, there will be some amount of fuel and oxidizer. So, this will be the mixture fraction. So, okay, in the mixture. So, mixture, and this is a definition of this mixture fraction. Okay. If the chemical reaction is completed within the combustion chamber, either, so now please understand, now chemical reaction is completed, either fuel or oxygen is consumed based upon the value of F and will not be present in the mixture. Okay. If, okay, so for example, chemical reaction is complete, that means if insufficient oxygen is there and it is consumed, excess fuel will be there in the product. If excess oxygen is supplied and fuel is consumed, then excess oxygen will be there in the product. Okay. Now, if at some location where, say for example, if there is excess oxygen supplied, some location there will be stoichiometric combustion. Okay. If F is equal to stoichiometric value, that means at that location there will be no fuel or oxygen, then both fuel and oxygen will be consumed. So, we have scenarios like this. So, let us say that is the value of stoichiometric. For example, here also, see here, this is the stoichiometric value. Let us take that first. When I say F equal to, for this definition of F, when I say F equal to F stoichiometric, that means I should not have any fuel or oxidizer in the mixture, correct. So, that means, see here YF will be 0, YO will be 0. So, this term will go out, and stoichiometric value of F will be the oxidizer side, YOX by S at the oxidizer stream divided by 1, that is the fuel mass fraction of the fuel stream, plus YOX by X at the oxidizer stream. This will be the stoichiometric F value, okay, by this definition what we have done here. So, this is the stoichiometric. But if there are two conditions now, if F is less than stoichiometric, what will be the mixture this? If it is less than stoichiometric, then what happens? Fuel will not be there in that. Fuel is consumed now in the mixture. So, other terms will be the same, the fuel will be consumed here. So, fuel YF equal to 0, you can note that YF is equal to 0 here. So, you have to put YF equal to 0 in this and write that situation. So, F is less than F stoichiometric. So, F will be defined as putting YF as 0 in the product mixture. Similarly, when F is greater than F stoichiometric, then oxygen will not be there, fuel rich mixture. So, YF will be there, oxygen will go to 0 in the product. So, this will be the definition. So, I now only trace the mixture fraction values and get this values, we can retrieve the value of YF, YOX etc. just by solving the mixture fraction alone. That is the advantage of defining the mixture fraction. So, now once I know, I do not need chemical kinetics as I told. So, the extent of diffusion or non-premixed flame is depicted by the contour of F equal to F stoichiometric. When I note the points where F is equal to F stoichiometry and connect them, then I get the flame shape. So that is the location at which the reaction takes place. So the several conserved scalars like yf plus ypr by 1 plus s or yox by s plus ypr by 1 plus s, anything can be used here. Similarly, the this h also defined like this. So I can either use T ref may or may not be used here. I can say just Cpt plus yf in delta Hc, or if you want you can add a reference temperature T minus T ref plus this, anything can be done. So now if you use this, then you will get another equation based upon the F. So this is for this. For example, when I write the enthalpy, okay, Cp into delta T plus Yf into delta Hc. Now we can say that Trf can be 0 also, reference temperature can be 0 also, 0 Kelvin. Okay. So in that case, I write the F like this. So you can see this. When I say M, this is the mixture. So mixture temperature Cp into mixture temperature minus reference temperature plus Yf at the mixture into delta Hc, okay, minus Cp into T infinity minus T ref. There Yf is 0, this is air side. So Yf equal to 0 here. So we can actually write plus Yf into delta Hc at the oxygen side, which is equal to 0, or this is air side, but this is equal to 0. So I don't include that. Similarly, in the this is the term where, see, you can see the Cp into Tf, T of fuel, here this capital F is fuel, Tf minus T infinity plus Yf into delta Hc, this Yf equal to 1 here in the fuel stream. And in the oxygen stream again the same term appears here because Yf is 0 there. So this will be the definition of mixture fraction. So now I solve for the mixture fraction without involving. So this conservation of same conservation like B variable, I can write a variable and solve for mixture fraction, which will not have any source term. So as I wrote the equation here for B, instead of B you substitute F here. So that will be the conservation equation for the mixture fraction. Solve that. Once you solve that, then you can retrieve the original variables. Okay. So you can see that this T infinity is the air temperature. I have given everything. So Tm is the product temperature, Yfm is the mass fraction of the fuel in the product stream, and T infinity is the temperature of the oxidation stream. Tf is the temperature of the fuel stream. So we have a separate fuel stream, oxidation stream, etc. So that will allow us, and until the combustion is complete, we will note at all the values at the function of x for this one dimensional problem, the value of f, and we can note exactly where the fuel and oxygen are consumed, and there we can say the flame zone is formed. Okay, now retrieving the variables. Once f is known, as I told you, when f is less than stoichiometric, Yf is 0, Yox equal to Yoa into that is the oxidizer mass fraction at the oxygen stream into F stoichiometric minus F divided by F stoichiometric. So you know the value of F as a function of x. Okay, so that is this F. So that you substitute at any location. I want value of Yox. This is at any x location. I want the value of Yox. I can retrieve it by knowing the value of f at that location, f of x. That f stoichiometry is known to me. So that Yox at the oxygen stream also is known to me. This is known, f stoichiometry is known. So when I know f as a function of x, I will calculate Yox as a function of x. Similarly, when f is greater than stoichiometry, stoichiometry, then I know that Yox will be 0 at that location, and it is the free fuel side. Okay, Yf can be calculated at a function of x as at any x, as with this relationship where f is as a calculated as a function of x. So once f is known as a function of x, then Yf is calculated as a function of x using this. I will retrieve the variables. Inert, for inert species, Y inert will be equal to Y inert at the oxidation stream into 1 minus F. I am assuming nitrogen, for example. So nitrogen mass fraction at the oxidation stream into 1 minus F. Similarly, products can be retrieved. Once you know inert, then use this identity to get the product mass fractions. That is it. So, that is the way you retrieve. Similarly, temperature. When F is less than F stoichiometric, then you see that F can be written like this. F as a function of x can be written in terms of this, okay, and you get this. Similarly, F is greater than stoichiometry, you can write this equation and get the values of T. Similarly, the flame temperature can be calculated with this equation. Okay. So, now once you retrieve this, I can plot the structure. So, you can remember this, I will go back to this and just show this, you can show the gradient. So, the temperature varies like this. This is flame sheet, fuel side, this is fuel side, oxidizer side, flame is formed, and you can see the depletion of fuel, depletion of oxidizer, temperature, maximum temperature formed at the flame zone, and the decreases towards the fuel side and the oxidizer side. So, this is the structure of the diffusion flame, which you get in the final slide. You can see here. So, now fuel is depleted, the oxidizer, this is the oxidizer side, this is oxidizer side, and this is the fuel side. So, fuel is depleted here to 0 where the flame is formed or the maximum products are formed. Similarly, oxidizer is depleted from the oxidizer side to 0, okay, and they react to form the products. Products go to both the sides. Similarly, temperature reaches maximum at the stoichiometric value F stoichiometric. So, even though you get the linear variation only you get here, because already we have linearized the problem, we have removed the sources. In practice, actually you will get some non-linear variation as I shown here. Schematically I have shown here, non-linear variation will be seen here, but it is fine, actually it is not so non-linear. So, here at least we get the location of flame properly and the distribution of the species, mass fractions and temperature. So, this simple chemically reacting system will be very useful to analyze the diffusion flame. So, this will with this will stop the equations, governing equations for the reactive flow.